Not recording. Oh man, the people at home. So this is a probability distribution, right? Function. We have for each outcome we've assigned a probability. So what must be true? Well, one thing we can check at least, just to do a little reality check, is that these add up to 1. Okay, so do it quickly. Make sure that they do. Did you get 36? Out of 36, again, one nice reason not to simplify your fractions actually is that in probability it's actually very often true that it's nice not to simplify our fractions for that reason. So we get 36 out of 36, which is good. We caught them all. Okay. By the way, one nice way of writing this out, if you haven't seen this before, is at least for 2 dice, the sum on 3 dice we need a 3rd dimension or something. But the outcomes for 1 die are 1, 2, 3, 4, 5, 6. And for the other die, the same. And then if we write in here coordinate pairs that represent each outcome, then we'll have accounted for every single possible outcome on the 2 dice by writing them in this form where we have these coordinate pairs. This makes sense? I won't do them all, but I want to give you a flavor of how this might look. And I think you also might, I think you also might like watching something that's going to happen here that's kind of cool. If you haven't seen this before. Right, whatever. So now if you're looking for, so fill this out. Of course there are 36 possible outcomes, as we already talked about. So which ones, like say we're looking for the sum on the dice to be 5. Well, those are this outcome, this outcome, this outcome, and that outcome. Do you agree? So that's kind of cool, and that just doesn't happen with 5, it happens with all of them. For example, where are the ones that add up to 3? Right? And so you can see the ones that add up to, you can see now, there's 1 way out of the 36 to get a 2, 2 ways to get a 3, 3 ways to get a 4, 4 ways to get a 5. Each diagonal has 1 more than the last diagonal. Except for 6. Except after 6, then we go back downhill, and you can see why, right? As we go to these diagonals, we get 6 on this diagonal, and then back down to 5, 4, 3, and then if we're to complete the table down in this corner where we have 6 and 6, we have only 1 down there again. So you get this kind of. It's always good to think of ways to organize our work in a way that makes our calculations easy. So we finally are ready after all of that. Once we have all of this, it's very easy to answer questions like the ones that were in your homework on this, like what's the probability you roll a prime number? Okay, well just add them up, right, which ones you like. So in this case, we're looking for the probability that our random variable is greater than 8. And so that's the probability of our random variable being 9, or 10, or 11, or 12, and sum those up for me. Go ahead, tell me what you get. What was that? 1036, yeah. 5/18, yeah, sure. Okay. So this is exactly what we meant when we said earlier, like, okay, well, what do we do in the case where we have a set of outcomes in the probability space that are not equally likely? How do we handle that? Okay, well, first we need a probability distribution function, like this. And then, only then, we can sum up the probabilities, right? It's a little different than when we have equally likely outcomes where we're just like, well, there are 11 outcomes, there are 4 different outcomes that work, so it's 4 11s. Oh, wait, hold up. They're not equally likely. We need to weight them by their probabilities. Okay. Have you played this game before? You win the prize, Francis. The nerd prize.
I'm sorry. I played it last week, so I think I would.
Yeah, that's good. It is a little bit stressful. It's enjoyable too, maybe. Actually, it's really a gateway game to other complicated German award-winning board games. And if you would like other suggestions for extremely nerdy board games, my wife and I have a gigantic collection of such games that have complicated rule sets and will keep you very busy for a long time. Yeah.
Also, going back to that picture, noting something about it. Even though it tells you to put the robber in the middle, it's good that they always put it at the edge. That's where it should go.
Well, they don't tell you to put. They don't. It's random. You just randomize it.
I think in the rule book it says to put it in the middle, but no one ever shows.
I don't know. I don't think the rule book says that, Francis. We're gonna go throw down with you on this. Actually, that may be true in the new rule book or something. I don't know. Maybe there's like. You want to play spades too? Yeah, I played spades. I love games. So, all right. The reason I put this up here is you don't need to know all the rules. The rules there are a lot of rules to the game. But one of the things I wanted to highlight is that in this game there are these tiles where you get resources from these tiles if you if you have a settlement or a city along these borders. So every time that an 11 is rolled, for example, the people on this settlement gain ore to their hand, which is like good in the game. That's all you have to know. That's good. Okay? Or when a 9 is rolled, the people on this tile that live on this tile get wheat. Okay. So the thing is, which would you prefer? I shouldn't say that. Which one will gain more resources more of the time? Yeah, the 9 will. What about the 9 versus the 5?
Wait.
Trick question. Yeah, they're the same. Look at our distribution, right? There are two. Sorry, we didn't say there are 2 dice in the game. Okay. There are 2 dice in the game, and when you roll them, the sum of the dice is what dictates who gets resources that time. So now the other thing that makes me think of this distribution, whenever I've played this game, is that right on here they've tried to be helpful and put these 2 little dots, or down here, 4 dots on the 9. And the more dots, the more likely that is to roll. So the people, when you're playing the game, you're like, okay, that's going to be more likely if you don't know math or something, right? But it's more than that. It's not just that it is more likely. It's exactly the number of 9s we expect to see rolled out of 36. It's actually, every time you play this game, you're actually staring at not just the approximate, but the exact distribution we just came up with for the sum on 2 dice. It's cool. 4 out of 36, 2 out of 36. It's cool.
Oh, I didn't know that. I thought it was there.
You thought it was just there. Yeah, now you'll change your life forever if you play Settlers of Catan. All right. Let's return. We got games we talking about. We got cards and dice. Let's talk about coins. We got to do all the probability things. Okay. So a coin is tossed 3 times in succession. So let's let the random variable capital X be the number of heads that you get. So what is the support of our distribution even? What can the capital letter X even be? How many heads could you get in this experiment? You could get 3. You could get 1 or 2 or 0. Yeah. So. Oh yeah. So let's start by making a table for this distribution. So we just said the support of our distribution is 0, 1, 2, or 3. What's the probability? Let's take each one of these in succession. Let's try and get a probability here. So how many ways, what's the probability, excuse me, of getting 0 heads? That is, what's the probability of getting tails, tails, tails?
Oh, wait, is that 8
3 times, yeah, 1/8. So you could talk about the multiplication principle here. You could list all the outcomes. There are 8 of them. You can do H, 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 T, 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 C, H, 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 H. Right? There'd be 8 different ways this could happen. And only one of them is T, T, T. Or you could think about the fact that, yeah, it's 1/2 times 1/2 times 1/2. There are a couple ways to get that answer. What other answer would you like to go for right away here? Yeah, what's that one? 1/8. What's the probability of 1? How'd you get 3/8? That's right. Yeah, you get tails, heads, heads, or heads, tails, heads, or heads, heads, tails. Or what did I say? Tail, whatever. You get it. Tail, tail, head. Right? Whatever I meant to say. There are 3 ways to do it. It could come on the first one, second one, or third. What about 2 heads? Now, how'd you get that? Yeah, you could reason through it the same way and be like, okay, well, it's this one, this one, this one. Or you could just be like, well, it's whatever the leftover is, because it has to add up to 1. So good job. We made a table. If you were to graph this is not super interesting, but you might plot 0, 1, 2, 3, 1/8, 2/8, 3/8. So you could actually plot these as points, I guess. It's not super interesting, but you could draw it that way, maybe. Well, can you put that away just for my respect there? Okay. And then if you wanted, you could do it this way, or you could also, some people might like to see kind of a histogram underlying this. Right? Now I've drawn those in a very specific way. It's not just like a bar graph. These are bars that have exactly a width of, if this is negative 0.5 and 0.5 and 1.5 and 2.5 and 3.5, then these have exactly a width of 1. And so the area of this rectangle is 1 times 1/8, which is 1/8. The area of this rectangle is 3/8. The area of this rectangle is 3/8, and the area of this rectangle is 1/8. Which means that the area in this diagram is not just cosmetic, it's actually informative, because the area needs to add up to 1, right? So the area is interesting. That will save that for next unit. We're going to come back and when we do our stat unit, that will be an important idea, this idea of the area of the distribution. Okay. Let's talk about the function rule now. Can we get it? The probability that x equals x is equal to, here, I'll do this part for you, you're welcome. Something over 8. Oh, this is so easy for you, maybe. I don't know. Yeah, let's wait for everyone else, Katie, for a second. Yeah, good job. Everyone thinking about what the rule will be. Here, I'll give you this too. We also need to support x equals 0 or 1, 2, or 3. What's the rule? Is the question. What goes in that numerator? You understand the task here. We need something that will generate. If you give me an x, like 1, this better output 3, right? Yeah? This is tremendously easy for everyone? Okay. This was very hard for my previous class, so today, so I don't know, maybe just a class room full of geniuses. But yeah, it's 3 choose x. In fact, you might recognize these numbers. 1, 3, 3, 1. You know, you've seen those before. Those are the binomial coefficients. Those are 3 choose 1. Of course, that's how we're doing this even to begin with. How many ways are there? Imagine doing this with like 30 dice. Coins, excuse me, whatever we're talking about. Imagine doing this with 30 coins, and then in our table we had like 17 heads. We're wondering, oh boy, how do we calculate that? Well, we'd have to calculate that numerator would be 30 choose 17, right? From among 30 flips, how many ways can we choose 17 of them to be heads or something? This is a much easier case, but I think we're done on this slide. Questions?
But it wouldn't be over 8, so it would be like...
No, that would be like 2 to the 30th. Yeah, exactly. It would be the denominator. Questions, comments?
Wait,
Yeah.
So it's 3 choose little x or big x? Big
Little x.
Little x?
Yeah.
What's the big x?
The random variable. So this is the probability that random variable big X equals little x. So these are the little x values here. Yeah.
So is the x sum 3 choose x little x or big x?
There's a little x. Here, I'll do that when I write big X for you from now on.
I literally just asked that question.
Wait, did you? I thought you were asking what the difference between the x's.
Okay, first I asked what you asked, and then I asked about the difference.
Alright, my bad, dude.
Hey, we're finally here. We can say what the multiplication of principle of, we should have said this maybe on day 1. You guys were all using it already, and I asked you to justify it, but I think we've come to a point where we believe it now, that you can actually multiply probabilities for the joint probability, sometimes this is called. A and B is how you could read that out loud, or A intersect B. You guys have done enough set theory notation to recognize that cap symbol. So a simple example of this would be, and now one word that we need to kind of unpack a little bit is this word independent, so we'll have to come back around that word with a little more language and help in the coming day or two. But so in this first case, though, I think it's pretty clear that really, to say it very quickly, independence just means that one probability doesn't affect the other probability, right? And when you're multiplying, they're like independent in the English language sense of the word independent, like they don't affect each other. So it doesn't need to be said in this problem, I think, and in many problems that we've been doing, that these are independent. We've got 2 jars. We're pulling a marble out of both jars. Clearly, if you get one marble from this jar, it's not like, oh, okay, well, everything's different now. For the other jar, all the probabilities change. No, no, no. What happens in one jar stays in that jar. It's just 2 completely physically separate independent events. So we don't have to say they're independent here. It's very clear because they're physically independent. So there's not much to say here. What's the probability that we get blacks from both? The first one is 40 out of 100 times the second one has 5 out of 25 total in the second jar. So there you go, right? Just multiply. Okay, whatever. Move on. No need in that problem to say that they're independent, right? It's clear. Now in this one, we've got a person. What's the probability of ordering a Frosty is 0.2. The probability of ordering a burger is 0.5. There, someone needs to say that these are independent because it's not clear to me that these probabilities might not affect each other. Maybe it's true that a person who orders a burger is the person who is far more likely to order a Frosty for whatever reason, right? Maybe that it really influences the decision somehow. I don't know. So that's important to say. If that is said in the problem, then this problem is not interesting. And we're done. The probability of them ordering both is that product, which is 0.1. But notice that these are different places, I know they both feel like, oh, these are both exact applications of this, but you do need to think about the way the word independence is used a little bit here. Here it's not needed to say that, but here you really, someone does need to tell you that these are independent because it's not at all self-evident for the problem. We good on that. We're finally giving you permission to multiply things. Yay.
If it's not said anywhere, I'm sure should we just assume independent?
No, you shouldn't. No, I mean, if it's a physical situation where they're independent, if you're flipping a coin and you're spinning a spinner or something like that, then I think we can say it's independent. But certainly, if it's a question like this and it doesn't say they're independent, no, you may not assume they're independent. If there's any remote possibility that they could not be influencing each other. Yeah. So it's a little messy in some of those situations. Well, it's worth stopping after having seen a little bit of set notation and reminding ourselves how to use Venn diagrams and how to illustrate sets and how to use set notation. So I have just 4 different diagrams here as an example. There's nothing special about them. It's important that you always include the universal set, which is this rectangle. Again, we're thinking about now probability. We're going to go flexibly back and forth between probability and area, right? We're kind of thinking about probabilities of areas in these pictures. And so the area of the whole rectangle is 1. And then we fill in the probabilities in between wherever we like. So I've illustrated these as nicely as I can. So this is the one we're just looking at, P of A and B, or P A intersect B. So that's shaded in here. You can see, understand. So I think you've seen, we've used this in other contexts in this class even, but A union B or A or B, you could read that as either one of those things. And that's like kind of, I would characterize that as like the MasterCard area. Okay. And notice there that it includes the probability that both occur, right? Make sure you're clear on that. Not A is sometimes written not A like that, or this, or AC, like the complement of A. Lots of different, I don't know what. What's the favorite way in AP Stat? This way? Okay, whatever. You see A prime, something, there are lots, and there are other ways too. There are other ways too. How many different diagrams could I have shown on the slide? I only selected 4. How many are there? How many regions are there? 1, 2, 3, 4, to which we can assign white or yellow. How many different Venn diagrams are there for 2 sets? Yeah, for each region, there are 4 regions, 2 colors for each, so there are 16 possible Venn diagrams. A fun challenge for you would be to draw them all and come up with a nice, like, Boolean set theory way of writing down with a description of each one. Some of them are really interesting, right? Like this one. Like, can you come up with a rule that, you know what I mean, like, that says that? You know what I mean? Like, some of them are interesting. There are only 16 of them, though. Right? I just picked a couple that are good. It's important, I think, also that we look at this Venn diagram. I knew Katie would like it. Okay.
Some of us just don't express it like you.
Yeah, exactly. I know. I appreciate this. Facebook, it should be replaced with whatever your favorite form of social media these days is. Snapchatter. I don't know what it is. Yes, thank you. That's where all the cool kids are hanging out. This is a little hard to read. Things you own, things your cat destroys. mic drop. After pass drop. What? Dogs, yeah, actually, I don't like that. I'm a dog guy. All right, well, your book likes to, did you see this in the homework last night? They like to talk about like, they like to talk about avoiding copyright infringements and royalties, fees that they might need. So they said like the certain candy colored, colored shell candy or something like that. And you're like, really? You don't know what you're talking about. So this is not, we're not talking about, this is just like some fast food restaurant that has Frosties, okay? You don't know. You don't know. You don't know. This could be any fast food restaurant.
I went to Wendy's yesterday.
This is going on the internet. I don't want to pay royalties. Okay. All right. Okay. So actually, so the probabilities here are 0.2 for a Frosty and 0.5 for a burger, and we're also telling you that 0.1 is the probability that they order both. Okay. Now, a lot of these would actually be somewhat interesting and a headache of a question to ask: a Frosty, but not a burger. But with a picture, these all become very, very easy. So let's start, actually, before we answer any questions, with drawing a Venn diagram. All right, so in the middle, we'll put 0.1 for the probability that someone orders both. Now, one best practice for Venn diagrams is that you should adopt too, is that anytime you label a region, you label the area of that region to its closest borders, right? So it would be a mistake to label this region 0.5 is what I'm saying. Even though I think I understand what you're trying to say, 0.5 captures the area of the whole circle. Do you agree? So, but let's not do that because it would be confusing. So what am I going to label this?
4.
Good, 0.4. And over here? 0.1, so that the whole thing is 0.2. Good. And then now, let's think about the universal set. Let's not forget the rectangle. What is the remaining region out here? 0.4. So that the total now, anytime if you've labeled the Venn diagram correctly, it should add up to 1, right?
Yes.
All right, so now I don't know how, I just made up these numbers. Is it likely that 40% of the time someone walks into this place and does not order a Frosty and also doesn't order a burger? I don't know, yeah.
I just want to say that yesterday when I went to a certain fast food chain restaurant with the red-headed girl as the figurehead,
Yeah.
I ordered a salad, so I did not order.
You landed here,
Yeah.
out in this region.
So as far as I'm concerned, the probability is 1.
For you, yeah. Yeah. All right, so now do you see how quickly these answers come now? What's the probability that someone orders a burger but not a Frosty? Well, we just need to point to the right region. 0.4. Be done with it. What about a Frosty but not a burger? What about neither? 0.4. I mean, if we did the work of drawing this picture, these are suddenly easy. Notice how, I mean, they would actually not, they would take you a couple seconds without, if you didn't have the picture, you'd have to be like, okay, so a burger given that they ordered a Frosty. Okay, now we need to slow down and say what that means. Okay, but in common parlance, you don't need to be like an AP stat person to know what this means. If I see you walking out with a Frosty, what's the probability that you also ordered a burger? Okay, well, my world now is this. I'm just in Frosty world, right? These people don't exist to me. I see you have a Frosty in your hand, right? You're in this category. So what proportion of those people who had a Frosty had a burger too? Isn't it obvious that the answer to this question is 50%? Right? Half of the people. Now, let's slow down though and say what we actually just did. Okay? By the way this is written is the probability of a burger given that you have a Frosty with this vertical pipe here, like that, is equal to, well, we just said it's 0.1, it's this region, that's the people who had both a burger and a Frosty, divided by all the people who had a Frosty, right, which is 0.2. So that comes out to 0.5, like someone has already said. And just to be clear, if you're coming up with formulas here, let's try and come up with a formula here. The denominator was the probability of just what? No. Yeah, the probability of F was the denominator, just the probability of F, this circle, right? 0.2. And the numerator is a little more complicated. It was 0.1. That's the intersection of the two probabilities. So we've just maybe developed a little bit of a formula just from our own human understanding of what it means to say this, about why this is our formula for this kind of probability we have a given in there. It's called a conditional probability, and the reason for that is that this is a condition that you're placing on the probability. Right? Give a name for it. And he asks, is the probability of ordering a burger changed by the fact that, like, if someone comes out without anything in their hands, I'm like, what's the probability they had a burger if I don't know anything about them? What is it? Given in the problem. 0.5. And what is the probability of a burger given that I see you have a Frosty in your hand? Ah, you have a Frosty in your hand. Therefore, the probability for you is, oh wait, it's still 0.5? If that happens, if these are equal, then we call these events independent events. That is, if you introducing the fact that that you had a Frosty makes no difference at all on the probability you had a burger, then we call these independent. And that's the word we've already been using today, but we now have a formal way of saying it. B and F are independent if the probability of B is equal to the probability of B given that F occurs. I hope that makes really good real-world sense. A lot of times the example I did this with my Algebra 2 class, and they were first learning this concept too, where you use the independence of them. And I actually surveyed the class and had them all give some answers to some questions, including, you know, what season of the year were you born in? What sport? Do you play sports or not? Are you a boy or a girl? Like all these different questions. And I asked different questions like, what's the probability? I had them work with the spreadsheet that we had generated, and I asked them, what's the probability that you play sports? All right, now what's the probability that you play sports given that you're a boy? Now, what do you think? Do you think those would be equal? No, let's not talk about how the world should be. But they weren't, right? It was very highly influenced, right? If you were a boy, it was far more likely that you played sports. But when we did the probability of sports, and what's the probability of sports given that you were born in the fall? Well, those were basically equal because it didn't really matter. Like if you came to me and you're like, what do you think? Do I play sports? And then you said, well, hold up. I was born in spring. I'd be like, that doesn't matter to me, right? Right? That wouldn't matter if you said, what's the probability of sports given that you played something? So that's called independence. It looks like we're done. Are we done? All right. Homework, whatever. 7 tonight, please.